Okay, by the way, so this will be the heap sort as well. For the heap sort, this is definitely a comparison-based sorting technique based on binary heap data structure to sort elements. The heap is a nearly complete binary tree where the parent node could either be a minimum or maximum, but we're dealing here with the maximum. The heap with minimum root node is called the minimum heap. The root node with the heap that's heap, okay, with maximum root node is called max heap. So for now here, the concept for binary heap, it is complete the complete binary tree. When we say complete binary tree in our data structures and algorithm, complete binary tree, you have to insert as left as possible. You will not be going, you cannot insert as right if you will not be able to insert yet in the left. So that satisfies the heap property. It is used primarily as an efficient data structure for implementing priority queues. The two types of binary heaps will be the max heap and min heap. So for this one right now, max heap, the value of a parent node must be greater than or equal to the values of its children. And min heap, the value of the parent node must be less than or equal to the values of its children. But we'll be only dealing with the max heap actually. Now, for the insertion, add a new element. That will be the operations for the heap sort. Add new element at the end of the heap that maintains the complete binary property. Bubble up. When you say bubble up, you will have to swap that into the um upper element. By comparing it to its parent, the element is more significant than its parent, then swap them. And afterwards, repeat that step through until the heap property is restored. Afterwards, here we have the deletion. You have to remove the root node, which the largest element, and replace the root node with the last element in the heap. So to maintain the complete binary tree structures, and you will bubble down. You will begin to swap that in the other element below that element by comparing to its children. If the new root node is smaller than any of its children, swap it to the larger child. So that's you can actually check that one in the video that I presented to you in the other separate video. Repeat step 3 until the heap property is restored. So for this one right now, heapify build heap. It is a process of transforming a uncertain array into a valid heap. I also presented a video different for this, and that ensures that the heap property max heap or min heap is maintained for all nodes in the binary tree starting from the last non-leaf node to the root. So there will be a from the last node there will be 1, 2, 3, 4, 5 as what I mentioned to you in that video. The heapify process works by calling the bubble down or sift down operation for each node starting from the bottommost node that has children working upwards. That's basically presented in the separate video actually. So for the heapify, build heap is the process of transforming an assorted array into a valid heap. And that ensures that the heap property max or min heap was observed. It is maintained for all nodes in the binary tree, starting from the last non-leaf node to the root. So the heapify process works by calling the bubble down or sift down operation for each node, starting from the bottom most node and working upwards. So that's how you will do it. Now the heap sort steps, you have to treat the array as a complete binary tree, then build the max heap. Heapify sort the array by placing largest element at the end of the sorted array. That's basically the few steps. For the time complexity that we are dealing here, the building the heap, there in actually in the time complexity, we are having here a specific the time complexity of heap sort can be analyzed in two stages. The first stage will be building the heap. The heap needs to be built first. This is done by organizing the array to a binary heap. Then building the heap takes a linear time because each element only needs to be adjusted a limited number of times, approximately of logarithmic n of time. So that's basically how does it work. So afterwards, the next stage will be extracting elements, sorting. So after the heap is built, we repeatedly remove the largest or smallest element from it and reheapify the remaining elements. So you have to really do the reheapifying afterwards. You were able to delete, then you will begin to bring that basically the lower part, then bring that up, then you have to reheapify everything. Extracting an element and reheapifying the heap will takes logarithmic of time. Since there are an element to extract this state, this step takes n log n time. So for this one right now, therefore we can conclude that the best case average and the worst case will be having the same time of n log n for the time complexity. For the space complexity, it will be the heap sort works in place, meaning it does not require additional arrays or structure to sort the elements. The only additional space used is for a few variables to manage the heap and the index tracking. Therefore, the space complexity here will be constant space complexity. So I'll be going to tackle the separate video will the counting sort as well.